Alright, so this is active filter design, lecture 41. In the last class, we were discussing ways of implementing this voltage controlled current source, right. We have already discussed why it makes sense to use a voltage controlled current source in practice rather than a voltage controlled voltage source. And the first implementation we discussed was that of a single stage transconductor, and we said that that is not particularly great because the transfer function of the integrator will be modified, and the only way in which you can get the ideal transfer function, so to speak, is to make GMR much larger than 1. In other words, you need to have a GM which is much larger than 1 over R, right, which perhaps takes a lot of power to realize. Then we said instead of putting GMs in parallel, which is what one means when one says a large GM, the other alternative was to increase the transconductance by cascading transconductors, and in principle at least it seems as if cascading transconductors should give you ideally infinite GM at low frequency, and beyond, as frequency increases, unfortunately the parasitic capacitance at the output of the this is what we meant when we said cascade to transconductors, right, and the poles I am talking about are the parasitic poles here, all right. And so clearly it is apparent that at low frequency you essentially get an infinite short circuit transconductance. The equivalent Norton current source at the output of this transconductor is simply GM1 times RO1, which ideally is infinite, multiplied by GM2. That is the short circuit current which flows in into the output, right, and that definitely is much larger than what you would get with a single stage transconductor, unless the transconductor happens to be infinite, right. At least you see the motivation for doing this. Then we said that, hey, if we did this and use this instead of the transconductor, the single stage transconductor, what happens is that when you hook it up as an integrator, one thing that is for sure is that as this resistance tends to infinity, one would in principle expect an ideal integrator no matter what this GM was, correct, because the unity gain frequency of this integrator is tending to very low frequencies, which is equivalent to saying I am going to remove this resistor and want to see what happens to this loop, right. Clearly your prior experience by now must tell you that this is an unstable system, or a system with poles on the j omega axis, because this is the familiar two transconductor gyrator, right. Okay, inductor, capacitor, two integrators in a negative feedback loop. This integrating capacitor is doing nothing, right, because there is no current flowing through it, which means that there is no voltage across it, correct. Then we said, okay, we have got to figure out some way of damping this loop, and the various ways we discussed were putting a resistor here. That does not cut it, because what happens to the DC gain? It comes down. What about here? Same thing, right. So what we said that it is indeed possible to hook a resistor here, but implement this as a transconductor this way, right, and then we see that putting it here or here does not make any difference, right. And if you now look at this contraption, it is now a transconductor which at high frequency basically looks like a single transconductor because this guy is too slow to react, right. Whereas at low frequency you have very high transconductance because this current will be dominating over this current. So, this is a way in which you have the advantages of both the high gain stage as well as the high speed stage, right, because this high speed simply because there are no internal poles. Okay. So, this is nothing but what is called a feed forward compensated opamp or an OTA. I mean, anyway, I don't know if I mentioned this the other day, but just like how a voltage controlled voltage source with an infinite gain is called an operational amplifier, right. Similarly, a voltage controlled current source with GM tending to infinity, normally it would be called a transconductance amplifier or a transconductor. Now, because the GM is tending to infinity, right, in principle it can't be used open loop, it has to be only used as the forward amplifier in a negative feedback system. Just like you cannot use an op amp open loop, it has to be used in as the forward path of a negative feedback system, right. And once you do that, you can do many mathematical operations, which is why you call it an operational amplifier. Similarly, if the GM tends to infinity, what would you think you would call it? You call this an operational transconductance amplifier or OTA for short. Please note that an OTA is very different from a simple transconductor. The simple transconductor that you use to build GMC filters, for example, have very finite transconductances, right. Whereas here the intent is not to have a finite GM, the intent is to have an infinite GM, so that when you build a negative feedback loop using these characters, the error voltage or the error quantity driving the forward amplifier becomes ideally 0 or in practice as small as possible. You understand? So, the only difference between an OTA and an op amp is the output impedance. An op amp is an ideal behaves in principle at least like an ideal voltage controlled voltage source with 0 output impedance, right. Okay. Whereas an OTA behaves like a voltage controlled current source, ideally its output impedance is infinite, right. Okay. Now, so this is an example of what is called a feed forward compensated OTA. All right. Understand? And another way of introducing the damping coefficient was this. Sorry. This is the integrator, and the stuff in the whatever green enclosure is the OTA, right. Again, as you can see, at low frequency the transconductance is virtually infinite, right, because GM1 flows into an open circuit, generates a large voltage which gets multiplied by GM2 and sucks out a large current, right. At high frequency, however, what happens? You can think of this as the CCS shorting of the second transconductor, right. So, thereby reducing it to a first order system. Does it make sense? Okay, and this is nothing but the classical Miller compensated circuit. Yeah, okay, whatever. All right. Now, if GM2 is much larger than, I'm sorry, if GM2 is much larger than GM1, what is the approximate transfer function between input and output? It behaves like a first order system, right? I mean, at least if I broke this connection, right? If there was no load here at all, this would behave like a first order system with a transfer function GM1 by SCC. Okay. So what is the unity gain frequency of this transconductor? GM1 by CC. Okay. All right. And what do you think will be the output impedance of this transconductor? It should be around 1 over GM2 at high frequency, simply because CC becomes a short, right. So, if you choose GM2 to be sufficiently large, I mean it is equivalent to saying that nothing much happens if I connect this here, right. In other words, this GM1 by SCC will still be valid if GM2 is sufficiently large. Of course, the expressions become extremely messy the moment you start to do, when you have to add capacitors here, here, perhaps here also, and go and do the maths to get the exact transfer function of this integrator with finite GM1, GM2, you know, C1, C2, C3 and so on. Just becomes extremely messy. One thing, and of course, if you need to do it, you can always do it, that is not a big deal, right. So, the only thing I am trying to do here is to give some intuition about what kinds of improvements one can expect when one implements the transconductor this way, the OTA this way, correct. All right, so let's try and get this straight. Can you comment on this potential? Ideally, what do you want that to be? Ideally, if this transconductance amplifier was infinite, this OTA had an infinite GM, then the virtual ground voltage, the so called virtual ground voltage, would truly be 0, right. In which case, the current flowing here would be VI by R, and which means that all that current has to go into the integrating capacitance C, which means that the voltage across the capacitance would be an integral of the input current, right, and the output voltage, which is the capacitor voltage, the negative of the capacitor voltage plus the virtual ground voltage, right. Is that clear to everybody? Would also be exactly the same as the capacitor voltage, because the virtual ground voltage is 0, which means that the output voltage would be nothing but minus of the integral of the input. So, all trouble, in other words, all non-idealities that you see at the output, right, can be traced to the virtual ground node not being 0 as a function of frequency. It is not just enough if it is 0 at one particular frequency, right. Identically, the virtual ground node must be 0, right. In the single stage OTA, what did you find was the virtual ground voltage? Let me call that Vx. In a single stage OTA, Vx is what? It is 1 by 1 plus GMR times Vi, correct. Hopefully, we are doing better than that here, okay. So, to get some intuition about what is happening, let us kind of make a few assumptions, right. One, if we are doing a decent enough job, even if this is not 0, this must be close to 0, correct, right. This is just to give you, I mean, to give you first order behavior, what to expect type of analysis. Similarly, if GM2 is large, what can you expect about that node voltage? This is nothing but a current controlled voltage source. In other words, you can think of that as an integrator itself, correct? Okay, as a single stage, what do you call, I mean, if I just only showed you this picture, you would immediately say it is a part of an integrator built using a single stage transconductor GM2, isn't it? And with an integrating capacitor Cc, right? So, which means that this node potential must also be close to 0. Now, can you comment on the voltage difference across, I mean the voltage across C and the voltage across Cc given these assumptions? Right? The voltage across the integrating capacitor of the integrator and the compensating capacitor Cc must be about the same, correct? If now, if the voltages across the two are the same, what comment can you make about this current versus this current? I mean, the voltage, I mean, it can't be the same current, correct? Because two different inputs. So, if I call this I1, what is the current through Cc? I1 by C times Cc. Does it make sense? All right. Okay. Now, where does this I1 times Cc by C, where must it be coming from? It must be coming from GM1, correct? All right. So, what must this voltage be? If GM1 is supplying a current of I1 times Cc by C, so Vx must be approximately I1 Cc by C times GM1. And what is I1 approximately? This must be I1, approximately V in by R. All right. So Vx therefore in our case is approximately Cc by C times 1 over GM1 times all right. It is all approximate analysis, right? The actual analysis is run to 2 pages because of all the capacitors and all that stuff, but this must be asymptotically true if GM2 is large, right? Okay. So, what is the moral of the story? First of all, are we doing better or are we doing worse? Or it depends? It depends on Cc by C. Okay. Now, what do you think? So, for a single stage amp, this is approximately Vi by GMR. Now, Vx is nothing but Vi by GMR times Cc by C. So, if you want the 2-stage op amp to do much better than if you want the 2-stage Miller compensated op amp to do much better than the single stage op amp or OTA, what should you do? Cc by C must be much smaller than 1. Okay. Does that make sense? All right. For noise reasons, what can you say about GM1 and R? Okay, all right. Can you let me reword the question? Finally, we want the noise to be dominated by the resistor, right? That's what we found in a good op amp RC integrator. Now, can you comment on the contribution of noise from GM1 versus the contribution from R. Okay.
So it will dominate more.
Which do you think is, or rather, what is the relative contribution of the noise of GM1 versus the noise of the resistor R?
Depend on CC by CC by C. It's same. It will also depend on CC.
Pardon?
All this noise will flow.
All what noise will flow through where?
Noise current of R. Noise current of R will get integrated by
Okay, all right. What about that of GM1?
Go through CC and 1 by GM1.
Through CC and also it will also get integrated.
Okay, so
Depend on CC by CC. Depends on CC by C. It will be 1 by GM1 R plus.
okay, let me attack this from another side. All right, so we want so forget about that stuff. So if you thought of this as a single stage OTA, right? I mean, finally, what do you want this voltage Vx to be? You want it to be much smaller than Vi, correct? Which means that Cc by C times 1 by Gm1 R must be much less than 1, which means Gm1 R times Cc by C must be much greater than 1. Sorry, C by Cc. Okay. All right. The next thing is, if you kind of consider the noise of this is say 4 kT eta times Gm1, this is Gm2, okay. So this noise source can be modeled as an equivalent voltage noise, where if the transconductor is pushing out or spewing out 4 kT eta Gm1, I can think of it as an equivalent noise voltage (4 kT eta by Gm1) in series with the voltage source, the input voltage, right? Which means, and as far as the resistor is concerned, what is the spectral density of this character? 4 kT R, right? And this voltage, if you have done a decent job, the difference between the input terminals of the transconductor must be roughly 0. So what must be the current flowing in through the resistor? It must be Vi. I mean, the noise current that must be flowing through the resistor is the noise voltage of the resistor plus minus noise of the transconductor divided by R, right? So now can you tell me the effect of transconductor noise versus resistor noise? At the output, what will be the influence of resistor noise? It will be proportional to 4 kT R. The transconductor noise will be proportional to 4 kT eta by Gm1, correct? So if you want the total noise to mostly come from the resistor, right, then what can you say about Gm1 and R? So which means that Gm1 R must be much larger than 1. Does it make sense? Okay, as usual, right? So this is telling you that if you had a 2-stage Miller compensated structure, right, when compared to a single stage OTA, you are getting an additional benefit. The noise is, remains the same, right. But if you use the same first stage transconductance, adding a second stage and compensating it with CC is effectively multiplying up the first stage transconductance by a factor C by CC. So we have two inequalities here, GM1 times R must be much larger than 1 and C by CC must be much larger than 1, which is equivalent to saying that GM1 by CC must be much larger than 1 by RC. Does it make sense? All right. Okay. So what is this? In English, what does this mean? The unity gain frequency of the integrator you are trying to make must be much smaller than the unity gain bandwidth of the op-amp that you plan to use. This makes sense, right? Intuitively, it makes sense because you can't, it sounds to be too good to be true that you can make an integrator with a large unity gain bandwidth using a cheaper op-amp which is very slow. What is the meaning of unity gain bandwidth of an op-amp? It is some index of how fast the op-amp can respond, right? And how is this negative feedback loop working? The negative feedback loop is working in the following way. It is monitoring the voltage at the virtual ground, right, comparing it to 0 and then whacking the output node in the right direction. That is basically what is physically happening, correct. Now, if the fellow who is supposed to do the whacking himself is very slow and relaxed, you understand, then obviously there will be a lot of error at the virtual ground node because the feedback element, the forward amplifier is not doing its job fast enough, all right. So, it stands to reason that you can't implement an integrator whose unity gain bandwidth is higher than the unity gain bandwidth of the op-amp, right. And as this analysis shows, the unity gain frequency of the integrator, if you are interested in doing a good job, must be much smaller than the unity gain frequency of the op-amp. Okay, and this also indicates that you must choose GM1. So when compared to a single stage OTA, you are getting an additional benefit. It is equivalent to increasing GM1 by. If you try to compare this to a single stage OTA, it is equivalent to increasing the transconductance by C by CC. Does it make sense? Intuitively the argument is what I showed earlier, right. If you had used only a single stage OTA, this transconductor would have to supply the entire, would have to, if this was not around, right, all this current would have to flow in or out of GM1, correct. Now, since all this current has to flow in or out of GM1, it stands to reason that the input voltage that excites the GM1 must be large. Now, what is happening? Thanks to GM2, right, only of all this current, only a small portion of this I1, right. So a lot of current flows in here, but only a small portion of that, which is given by I1 times CC by C, is required to be provided by GM1, right, which basically makes its job easier, which is equivalent to saying that its input voltage now has to be smaller, which equivalently means that the integrator is tending towards ideality in a lot better sense than it was when you had only the first stage transconductor. Okay. All right. So implementation wise, we were talking about this when the last class ended. So, I will only draw half the circuit. All right. This is the Miller compensating capacitor, and as usual, when we know all the bad things that RHP zeros can do. So, what do you do to get rid of the RHP zero? You put a resistor value is CC 1 by GM2. Does it make sense? All right, and we were talking about how, I mean, at least one straightforward way of implementing this is to have a common mode feedback loop which goes and tweaks the output common mode voltage of the first stage to be some known quantity, and similarly you have CMFB2 which goes and tweaks this current source as well as the other symmetric current source corresponding to the other side to keep the output common mode feedback output common mode voltage same, right. One advantage you can straight away see of this approach is that the output voltage can now swing. You can go all the way up to VDD minus delta V on either side, I mean delta V on either side, right. So, the peak to peak swing possible at the output is now VDD minus 2 delta V, correct. I mean presumably you can't do better than this, correct. You are just losing 1 delta V on top and 1 delta V below, all right. So, the advantage of using a Miller compensated op amp is the really good utilization of the possible supply swing, right. You are not throwing it away and wasting the supply on whole bunch of transistors who are not doing any work, right. It really I mean you lose only the bare minimum needed. Okay. Now, one question that was asked was, do you strictly need 2 common mode feedback loops or can we do with 1, right. To motivate that, let me just look at this and then try and explain to you why the question makes sense, right. So, to set the output common mode, right, all right, or to vary the output common mode, which all knobs do you think I can turn? Obviously, one I can turn is to vary the output common mode, I can tweak this guy. So, when that node voltage goes up, what happens to the common mode voltage output? Comes down. Okay. Do you think there is anything else I can do? Gate of the PMOS. Okay. So, if I yank that voltage up, what happens to the output common mode? Pardon? If I yank this up, this goes down. If this goes down, this goes up, right. So, there seem to be 2 knobs through which I can go and tweak this. So, one strategy could be to avoid the bother of having to have 2 common mode feedback loops and do this, which is sense common mode, right, and then use an error amp with the proper sign and then go and tweak that voltage, correct. So, if the sign of the negative feedback loop is right, in which case this must be positive and this must be negative, or is it the other way around? The other way around. Okay, sorry. Yeah. Okay. And the usual same old, I mean, error amp and so on, right. So, if we did this, then there is obviously the output common mode voltages is set to VCM ref, right, but there is another benefit. What do you think is this voltage? What should I do to this character now? So, all that I need to do is make this a fixed current, right, alright. So, if I apply common mode feedback here, what do you think is this voltage? It is simply VDD minus, I mean the fact that this voltage is sitting at VCM ref means that this current is exactly the same as I2, which means that its gate source voltage must be mod VTP plus square root of 2 I2 divided by mu n Cox W by L of that transistor. In other words, its source gate voltage is very well defined, which means that this potential is also well defined, which is equivalent to saying that if this potential is well defined, this is also well defined, which means that this common mode voltage at the output of the first stage is also well defined. In other words, you are using, I mean you are not applying individual common mode feedback around each stage, but you are using one common mode loop to set the output common modes of both stages, because we know that in this particular circuit the output common mode of the first stage also changes the output common mode of the second stage. The reason is the second stage has no common mode rejection, because it is nothing but two common source amplifiers without the tail current source in a differential pair, which gives you that common mode rejection. Alright. So, this as far as stability of this common mode loop is concerned, you see that this again, as far as common mode signals is concerned, this again behaves like a Miller compensated structure, and then there is the usual error amp. In fact, now you do not even need this amplifier to have large gain at all, right. Okay. Yes.
We don't worry about common mode rejection ratio in the second half because we assume it's been rejected in the first.
Yes, yes, yes. Yeah, so that's a good point. So the question is why, how come common mode rejection is not important in the second transconductor? It's not important presumably because the first stage has already rejected most of it, right. So, alright. So, yes.
Why it is not triggered by the error amp large gain? Because last time we saw that even if the loop gain is high, the error amplifier.
Right. I mean, if you now go end up putting a large gain here, you will find that you are introducing an extra pole, which causes now becomes a third order system, becomes extremely messy, right, and probably difficult to compensate. So, it is simply straightforward to have a low gain error amplifier. There will be finite offset between the common mode reference. Yes, yes. Okay. So, anyway, this kind of common mode control has several problems, which is why a lot of people do not use it, right. It is a subtle problem and it is not immediately obvious, and it first came out in practical, I mean people did start doing this, and then I found that in some of their chips once in a while the whole op-amp, all the op-amps would simply latch up, and the only way to get them out of this kind of behavior was to turn off and turn on the supply, right. And the reason for that was, if for some reason, let us say the input pair does not come up first, right, when you are turning on the chip, different nodes come up at different speeds. So, if the input node if the input pair does not come up, in other words the two gate voltages here are too low, what do you think will happen to the output common mode? It will be either I mean, so what happens is that the output common mode, let us say starts off at 0, right. The common mode feedback loop is telling you that the voltage is too low, it needs to be pushed up. The only way that can happen is when the this node goes lower high. If the output common mode voltage is 0, right, the only way to push it up is to yank the gates of the PMOS devices. Unfortunately, the input NMOS transistors are off. So whatever you do at the gate of that node, I mean whatever you do at that node, it does not matter because the gates the lower current source is off. You understand? So the output common mode will get stuck at will get stuck at 0, right, and unfortunately in filters what happens is that the output common mode of one is the input common mode of the other. So if this output common mode does not come up, right, the input common mode of the next one has also not come up, which means that the output common mode of that is 0, right, which now feeds back to the input common mode of this. I mean, you understand what is happening. We said that just like in a GMC filter, an active RC integrator, I mean fully differential active RC structure, while there is negative feedback for differential signals, for common mode signals there is positive feedback. Two identical op amps, if I yank the common mode of one, let us say the output common mode goes down, right. If I put 2 in cascade, whatever the sign of the common mode gain is for each of the single stages, when you cascade 2, the end to end gain will always be positive, correct. So if I now had 2 integrators like this hooked up in a negative feedback loop for differential signals, it does not help me that there is negative feedback for differential signals, because for common mode signals there is positive feedback. And you can see that this is a disaster waiting to happen, right. So if the input common mode of the first is too low, the output common mode of the second stage will also be very low. If that is too low, right, that will be the input common mode for the second integrator, that is cut off now. The output common mode will also therefore be 0, which in turn is the input common mode for this character. So everybody is happy, you understand, right. So this is a stable situation, right. So this is a problem with using op amps, using one CMFB loop for both stages, right. So you can get stuck in this all 0 state, in which case it does not matter even if you design the world's best filter, it just does not start, right. Like it's like having a BMW but without the spark plug, it does not help you, you understand. Yes sir.
Eventually the overall input will propagate and
I mean that's what you are hoping, right. I mean so the this thing is that, okay, what if the okay, now but there is also the input to the filter, right. If now I kind of wiggle that around, hopefully it will get out of this state, but that's now taking a risk, a big risk, isn't it.
so is it a stable state like
This is clearly a stable situation.
as long as the inputs to the
Yeah. So I mean now you are hoping that not only is the input common mode what do you call you must make sure that the input common mode is high enough such that this turns on. If it does not help. You understand? The argument was that anyway you are forgetting about the whatever, right. So this is roughly the equivalent for common mode signals, right. So what he is saying is that okay, what about the input here, right. If I yank this now, will this guy get out of trouble, right. Please note that if this is 0, right, unless this is 1.8 volts, this will not go to 0.9, you understand. So unless you really wiggle, right, it will not get out, okay. So this is a very practical problem, and chips have failed because of this, right. And unbelievably, so there is a fix around this, you can still have this, and then you need the problem, as you can see, is that when the output when this guy is cut off, this there is no communication, but one part of the loop is like physically cutting the loop, right. So it doesn't really matter if the common mode feedback is the error amplifier is going crazy, right. There's just the loop, there's no loop to go and fix, correct. So you can think of some circuits which will go and go and kick this node even when the input pair is off, right. And in fact it turns out that trick, right, turned out to be one of AT&T's most money making pattern, right, because everybody was doing this and then all of a sudden chips would not turn on, right. I mean you turn on the supply and oops, no signal, right, the common mode is set to 0, right. And so yeah, right, and there is a paper in 1983 or something like that, but it's came out of Bell Labs, right, where they recognized the problem and fixed it. All right, and this is especially relevant in continuous time filters where you have common mode positive feedback, okay, even though there is differential mode negative feedback for the integrators. Does it make sense? Okay. So now, so that I would think concludes most of the stuff on active RC filters. I want to add to a couple of minor things on noise and active filters. We have seen only stuff in GMC filters. We have not seen stuff in active RC. The ideas are largely the same, but I would like to have a discussion on that. See, there's a meeting in this room at